This conference will now be recorded.
All right. So I wanted to cover a couple of quick topics. Our agenda today is Mudassir and Anu and Javi are going to talk about a cost model, right? Like this, all three of you, right? I hope I have that right. I'm sorry if I don't.
You do.
Yes.
Okay. There are three things I want to cover just before, because I think it's a really hot and heavy topic, and it's easily going to take us all the way through 9 a.m. Thing number one is we've got the storage workshop next week. So in fact, I think we're kind of interested in if you'd like to moderate a session and you have some knowledge of the POC and the storage and can help steer conversation, get in touch with me or JP. Second, thanks to Elad from Blue Cheetah, we've made some really good progress on the Bow electricals. So we're fairly close to ratifying them. I know that Anu, you guys are going to send something in. I think we're flipped over to something will change only if there's sort of convincing evidence that we should change. But please, if you haven't seen the spreadsheet, if you'd like your organization to get a voice in, please take a look at it. And we'd really like to bake them in. Finally, a quick word about the November summit. So we were allocated half a day. So the original plan when we made the plan for the papers, etc., was a full day session, and we were allocated half a day, which actually turns out to be one of the largest allocations in the for any track in the summit. So it isn't what we planned, but it's certainly larger than virtually everything else. But the consequence of this has been that we've had to prune the schedule. A number of talks have to be compressed into short talks. We had I'd say 4 interesting proposals for panels. I've had to say no to all of them so that we can combine them into one proposal, one panel, which we're working on. I've had to turn down a couple of work stream updates. That becomes a separate panel. We still have room for about 3. So overall, our schedule looks like this. We've got a panel, which is a work stream update. The second thing, we've got a bunch of really interesting technical talks. That's part 2. Part 3 is lightning talks, which many of you would have received invitations to. Tom Gregorich, I got to sync with you offline on this. And 4 is a panel which we're working on. So that's roughly our agenda. If you've received a letter, an email which says, hey, sorry, we didn't get in, I'm truly sorry. I'd like to find some way to accommodate your talk in our Friday meetings around the summit. Those are the 3 things I wanted to say about the November summit. DJ, anything else you want to add?
No, Baki, I think you covered everything well. I think we have basically 2 panels, an opening panel and a closing panel, which strives to absorb everything which everybody tried to present or submit. So I think agenda looks exciting, and yeah, nothing more to add, Baki.
It is a really, there's an agenda you will learn a lot from, hopefully. All of us will learn a lot from. And we've tried to fit as many people as we can in. Bill, I have to sync with you offline. I think everything else is in order. So I'm going to hand it over to Javi, Anu, and Mudassir, who've made some tremendous progress on a cost model. Tawfiq has graciously agreed to slip back by a few weeks for us to review this cost model for the rest of us to discuss it. So whenever you're ready. Does anybody have any questions? Because this, I can guarantee you this is going to take the next 50 minutes. So if you have any questions that you'd like me to answer, now is a really good time. Or you can reach out by email.
Maybe a very quick one, Baki. You
Yes,
mentioned the papers. Like, are you going to discuss them here, or do you want us to submit something? Like, I mean, like, how you're going to decide on the papers?
No, we've decided the session has been assembled. You're talking about the November summit, right?
Yeah, November summit, yes.
Yeah, so we've assembled the session to within the constraints of the time and the time we do have and the topics we want to cover. So for everybody who didn't make it, what I'm going to do is find a good way to accommodate you in our Friday meetings, or we're going to hold a couple of other workshops in those as well.
Okay, thank you.
So Bobby, this is Bill Chen. Talk to you offline.
Yes, please.
Okay.
Okay. Who gets the screen? I don't think I need to do anything, but anybody else?
I can present, but it says to share, ask the organizer to make you the presenter.
Yeah, 1 second. That's what I was worried about. How about now?
Yes, now I can.
Any other opens? All right, then I'm going on mute. It's all yours.
All right, thank you, Bobby. Can everyone see the screen? Anyone?
Yeah,
Yes.
it's kind of weird. It's kind of really, yeah, I
Me?
guess I've got my people bar at the top. So yeah, if
Is
you
it
could
Yeah,
make
we
it
clear?
can
maybe
see.
slightly larger, that would be nice.
And you can zoom on your own screen as well. On the right side, there's a plus minus.
Oh yeah, thanks.
Yeah, we can see it well. We can see it well.
All
Yeah,
right,
thanks, Elko. That would
sounds
help.
good. Thank you. So exactly as Bobby mentioned, this is a joint collaboration work between myself, Anu, and Javi. And it was born out of discussions that we were having within the business work group on essentially developing a simple but detailed enough cost model that can help everyone do trade-offs between one option of doing chiplets versus monolithic or multiple chiplet options and whatnot. And the assumption is that most companies may have their own internal detailed proprietary spreadsheet type models. And we're not going to make this as detailed, of course, but the intent here is to have at least a common model that everyone can use. And the data that goes into the model will be proprietary to whoever uses it. But the model is something that we could at least agree upon and have a number of factors incorporated in it that can give a first order of magnitude comparison between different options. And we would preface this by saying this is by no means the perfect model, and it's essentially a volunteer effort between the three of us in trying to enhance it and put out something that we feel could be a good starting point for everyone. And we're sharing this with more people because we would like to get inputs. And after the call, anyone who's interested, we will be able to provide a link to you, and we would appreciate the feedback that you could provide to us so that we can continue to enhance it. We've adopted a simple Google Sheet as a starting point so that we can actually have this easily scalable and more people can use it. And over time, we will add more functionality into the model and eventually make it something that could be even more sophisticated and could be used as part of the design process itself. As you notice, at the bottom of the sheet is a bunch of tabs, and what we'll do today is we'll go through each of these tabs and walk you through the model. And we would welcome, initially, please give us some time to go over some details of the model because we may address some questions that come to your mind, but then we'll leave plenty of time at the end for questions and inputs. And we understand that this is complex, it has a lot of factors in it. We won't be able to go through everything in today's meeting. We will introduce you to it, walk you through it, but when you go through the link that we will provide later, I'm sure more questions will come up and we'll be happy to address those. So to begin with, at least as a visualization, we've put together this simple flowchart to at least give a sense of how things are put together the way we're building the model. And Anu will walk us through a little bit on this flowchart and how essentially things are put together, and then I'll go through the rest of it. And then Javi will help out in terms of the use cases and the test part as well. So Anu, do you want to talk to this overall flow briefly?
Sure. Thanks, Mudassir. As Mudassir said, this was something that came up with at the business work group, and it was the #1 action item coming out of the meeting in April. And luckily, Mudassir had a head start on us, and so I was happy to jump on that bandwagon with Javi and make more progress. So it's been a great learning experience, to be honest. So this particular chart essentially shows you how we try to incorporate all the aspects of test yield into the overall flow. So if you look at the left side, we start with, just sending the GDS to Foundry. The wafer gets processed, all of that wonderful complex stuff happens. And then essentially the process of trying to get your known good die, or as we call it, pretty good die. Javi came up with that because it's not exhaustively good die. These are not 100% tested, much as we would like them to be. So as best as we know, those are good die. They come out of a probe testing with either a single or a double insert, and we have a cost associated with the number of seconds that the device is going to be in the tester and the loaded cost of that tester. So you can associate a certain dollar amount with each probe that you do on a die. Post that, you assemble it, and post assembly, of course, now you've got to do your final package testing, and that goes through as even with monolithic, the standard package testing, scan patterns, whatever else needs to be done. And then there is an element of retest where you can recover some of your yield. And we worked through with Elko and Swami to make sure that we sort of captured the high level aspects of everything. There is the devil's in the details, but this is, as Mudassir said, the first pass high level analysis. At the end of final package test with some amount of yield retrieval with retest, we get what are called parametric good units, because again, you could have some issues with some of the units in that. Assuming you get your good parts out of it, you move into what we call system level test, which is putting the part into the use case environment. In some cases, these parts need burn-in testing. In other cases, they don't. So you can put an additional cost for burn-in testing. In other cases, you can skip directly to your final test. And at the end of which, in the rightmost purple box, you've got your actual known good parts, which are good to go on the field, and hopefully with very minimal chances of failure. So just to show you at a high level, these are the three: the probe, the package, and then the final system level test is the test cost we have incorporated into this flow.
Perfect. Thank you, Anu. So we will go into the output of the model first and show essentially what we're trying to share or inform the user about. And then we'll go into the details of how we came up with the inputs and the factors and whatnot. So the output of the model is essentially in the summary tab. And what you see here, I will make it just a little bit larger, is normally you would like to compare two options. And the model is set up in the way that you can compare two options. It's a pairwise comparison. Now you could always save this sheet into multiple versions and compare option 1 versus option 3, option 2 versus option 3, 4, 5, however you want to do it. But the basic model is a pairwise comparison. It's comparing two options. And what you see here in the top section, these two sections, the top two rows 1 through 20, are focused on total cost, and then the bottom ones are focused on unit cost. And the cost is broken down comparing option 1 versus option 2 over a period of 5 years between the material costs, the NRE, the known good die costs, the quality, operating cost, IP interface cost, and any miscellaneous costs, and then the total. So these are the costs, the total costs that would be incurred for each of these categories for option 1 versus option 2. And this essentially shows the percentage contribution to the total of each of those costs for option 1 and option 2. And at the bottom here, it shows the unit cost. So for example, in this case, we're saying, for option 1 in this hypothetical use case, the unit cost of the device would be around $1,000, going all the way down to $900, whereas for option 2, it would be $570 going all the way down to $507. And then this is the breakdown dollar contribution to each of those costs. And you can see at the bottom here, you also have gross margin dollars, gross margin percentages, if you're selling this device to somebody and you have a certain ASP that's input. And this is a cost difference between the two options over the 5 years, which is plotted over here. This is the total cost and this is the unit cost. And what this shows is, for example, in this use case, this option 2 is significantly cheaper than option 1, And that cost difference between the two tends to show over a period of time, which also takes into account the shipment volume. So the unit cost in this case, as you can see, goes from $1,000 to around 900 for option one, in this case, which may be monolithic, a single die, and I'll walk you through this particular example. And then for option two, you can see that the price is significantly lower. So the intent here is that you can do an easy comparison between two scenarios and understand where the biggest bang for buck is coming from. It could be because of materials, it could be because of KGD, because of NRE. In this example, 87% of the cost is primarily because of BOM, just the material itself. And then subsequently, the big one would be the KGD, followed by the NRE, and then other things that add up. So this is essentially the output that we expect to give to any user, and they can use this to determine whether this difference between the two options is worth it or not. Maybe it may be, in this case, for example, we had an ASP of $1,000. Obviously, this year one cost is higher than $1,000, so it's very expensive, maybe prohibitive, and the most you may make in gross margins may be 9.89% if you're selling this device for $1,000. So lots of trade-offs and decisions can be made by using this type of a setup. And what you'll also have the ability to do is to download this as an Excel file if you want, and you can do like a one-way or a two-way data table or a sensitivity analysis that you have in Excel that you may want to use to say, what if my yield changed by 1% or my ASP changed by a certain 5 or 10% or my KGD changed by a certain amount? What would that do to my overall costs and what the benefit might look like in each of those scenarios? So that's essentially the output of what we're trying to deliver. Now, the way this runs is the inputs to each of these, option one versus option two, are entered in these tabs at the bottom here. There's one data tab for option one and a second data tab for option two. Now, before I go into the data tabs themselves, we will go very quickly over the factors that we've included into all of these inputs. And these are the factors that we've captured over here from the beginning. We take into account the assembly configuration, the number of chips that you're using, whether they're passive or active, the assembly sequence, the cost of assembly, the silicon node, the unit price, the demand, the probe time, tester and prober rate, final package test, KGD, PGD, SLT, test steps, test yield, test unit price, test unit yield, substrate price, power consumption, thermal cooling cost, IP interface cost, timeline, overall quality over time, quality cost, functional test cost, and then ASP and NRE. So total, there are about 28 or so variables that we've captured into the sheet, which go into data option one and option two. Just as for information purposes, this is the list of authors. So it's the three of us for now, with contributions from others that we've been getting input from. And here's a list of all the different versions that we've gone through, and we're at version 10 at the moment. And we'll go through a few use cases. So let's go deeper into what the data input options look like. So right now, the way it's laid out is starting from the left, you can enter as many as 36 different chips on a package. You always start with the substrate as the first one, and then you can enter any other number of chips. The color coding of each of these cells is described over here. So this color is user input. This color is calculated values. You don't need to change those. These are computed values, but if you wanted to enter your own, you can enter them as well. It won't break the model. And these are just the labels. So there's obviously, as you can imagine, quite a bit of user input that's needed. And it's important for the user to understand what they're entering, as with any model, garbage in, garbage out. So it's important to make sure you know what you're putting in and know how that might affect the model. Here, this is purely for informational purposes. You can enter active silicon or passive silicon, like an interposer or other pieces. This is the silicon node. So in this particular example, we're doing a 5 nanometer silicon die with about 16 nanometer chiplets. So this use case is a use case that Elko had kindly provided as an example for us. So we're doing a comparison of two scenarios in this one example, where we have one main die on a large package, and there are 16 small chiplets around it. And we're comparing this scenario with another scenario where we split the main die into two dies. And we want to see what the difference in cost is. primarily driven by the yield of this large die and what would happen if you split it into two. So this one option you're seeing here, data option 1, is showing one large 5 nanometer silicon die. These are the dimensions of the main die. And these are the dimensions of the 16 peripheral chiplets that are around that main die. 300 millimeter wafer, the saw street dimensions. There's usually some kind of a discount if you want to apply it on the wafer annual price. You can enter that over here. And this is the year 1 through year 5 wafer price that you could enter based on whatever communication you have with the wafer foundry. This is the NRE for the design and development, in this case for the substrate, for the active die, and for the 16 chiplets. This is the ASP if you're actually planning to sell this to someone else. And this is where we have a yield model for the die. And there are two yield models that we've incorporated. One is the Murphy model and the other is the Bose-Einstein model. And you can select whichever model you would like by selecting Murphy or Bose-Einstein over here. And for both the Murphy and the Bose-Einstein model, you need a defect density. So this is where you enter the defect density parameters. In this simplistic example, we're keeping the defect density the same, but as you know, over time for a given silicon node, the defect density tends to decrease, and you can adjust those values as you get them, or you can discuss with your partners on what the most suitable values are that you would enter over here. We would compute the die area. We would compute the effective area of the die, taking into account the scribe line, and then based on the wafer size, we would compute the gross die per wafer. Here we would have probe time, including indexing, tester and prober rates, dollars per hour, probe cost, and then here we would actually compute the yield based on the inputs that were entered earlier for the defect density using either the Murphy model or the Bose-Einstein model. Here we would then, based on this yield, compute the, take the wafer price and the yield into account to compute the forecast unit price. You would enter the forecast demand over 5 years for each of these devices. And then here we would go through an assembly sequence, which would be essentially binaries. You would enter 0 or 1. We've arbitrarily established as many as 7 assembly steps. So for example, in this case, we're showing that everything will be assembled at the end. So you have ones at the end, and that would compute your KGD. But you may have a scenario in which you may have, 3 dies mounted onto an interposer, and then the interposer is mounted onto a package. So you could basically have zeros over here, and then you have 1, 1, 1, 1 here, and then another one would be here, for example.
Very quick question, if you don't mind.
Yes, Tawfiq.
Like, do you cover in your model, do you have anything for yield recovery? I'm thinking, like, if you have a large die, you might, very large area, you might have a lot of dead cores. So it would tend to say, the bigger the die, the more you want to break it. But if I can, for example, do some recovery mechanisms by which I put few extra cores or stuff like that, can your model comprehend something like this?
Not in this version, but we've talked about it. So that what you're referring to is what is commonly called repairables, right? You may add redundancy in cores so that even though the base core may not work, but you have some redundancy, you can still utilize them.
Right.
We are cognizant of it. There are a few unknowns in capturing that, but it is something that's on our roadmap, and I'll talk about it on what the future features are that we're looking to incorporate. But in this current model, we don't have that.
Okay, very good, thank you.
So we go through the assembly sequence, and that essentially helps compute the known good die. And there's a small example here that we've created just for you to comprehend, because this is something that's a trouble for most people in how you can compute known good die. And so this walks through some examples of steps and how that's calculated. And again, if you start playing with the sheet, you will have a more intuitive sense of how it's set up. The values on the top here are input values on what you are expecting is the yield for each assembly step. So for example, if you're mounting 3 chips on an interposer, you will talk to the OSAT or the device integrator, and they can tell you what the expected yield might be, and you can enter those values here. And subsequently, you can play around with them and see how sensitive the final output might be to those values as well. Package assembly cost, final package test cost, final package test yield, SLT cost, SLT yield, And there's a submodule here, which Javi will talk about a little bit more about how the test part is captured in the overall cost details. Javi, do you want to talk about it?
Sure. So what we've allocated here is opportunity for 2 packaged test opportunities. So, number of seconds, it's simple, number of seconds, number of insertions at that site, and the loaded rate. And that loaded rate should be for your prober and the tester and all that. That'll be for final package test. And then similarly for your system level test, same sort of thing. You have a number of seconds that you would estimate, the number of sites that you'd have in parallel, and the rate that you'd have there as well. And again, that rate should be fully loaded, and it will come up with what your test times are, and it'll insert them at the right stages in the cost model.
So Javi, for the final package test, does it all, I'm not seeing it, but does it also allow for parallelism?
Yes, so the number of sites is there. So right there, that second line says number of sites, insertion number 1, and then that's in
Got it.
cell EF. Yeah.
Thank you.
So that happens. Yeah. So you have parallel for all 3 of these.
Great, thanks.
All right, thank you, Javi. And then this is quality unit DPPM, but this is aimed at final quality. This is not yield related. This is when you've built the device, you've shipped it to an end user, and the end user is now running it over a period of time. What is the expected failure rate that they would anticipate for this device, and the DPPM targets that you may want to achieve for it? And then there's operating unit cost, power, and thermal. This is again more from the end user's perspective, which would be how much does it cost for them to run the device, which is a combination of the power that the device is consuming as well as the cooling solution that's used to cool the device. And again, this is not something, if you want to, you can incorporate. If you choose not to, you can just zero out the values. But it gives you a sense of the end-to-end cost of actually operating the device as well as cooling the device. And then these are just the summations. The other important part that we've included is IP interface cost. And this is the royalty, the IP cost that you may be paying. Either you're developing it yourself or you're buying that IP from someone in order to have the chips communicate with each other. That cost is broken into 2 categories. There's a lump sum price you may pay for getting that IP. And then that sometimes if you're selling this device to someone else, there's a percentage of ASP that you're paying in royalty. So you enter both of those values here, and then they're summed up in the IP total interface cost calculation. And from here on out, everything you see that's this color is essentially calculation. So it computes the IP cost, the miscellaneous cost, the quality cost, the material cost, the KGD cost, and then it sums everything up into a total cost over 5 years, which is what you end up seeing on this summary tab, and has all of these values captured over here. And it does this for both options, and then the delta is compared on this summary tab. So that's where you see option 1 and option 2 information. And going back to the factors, so these are the factors that we've currently captured, but we have a parking lot over here, which essentially is the list of additional factors that we will be capturing further down the line as we start getting inputs and data from others, as well as help from folks who would like to try and do this. One of those includes reliability. This is long-term reliability of the device. We've only captured quality, but we haven't captured the reliability piece. Self-repair, redundant cores, which is what Taufik was asking about. We've already captured some of this, but there's some discussions around development costs and whatnot. So we would, if there's more detail, we can go into that. And some additional factors that Elko and Swami also provided, which is like RBOM, which is cost of passives and other components that go in. That's something that we plan to add into the tool itself, and a few other things that we may want to capture. We've captured some of these already. Some we would just want to make sure that they've been captured correctly. Now, one of the things that, sorry,
Go ahead.
is there a question?
I'm sorry, go ahead. I interrupted.
No, go ahead, please.
I guess of all those factors you're modeling, I'm just curious, would you agree that probably yield is the biggest factor?
Yes. So what you see here, you can tell from this, in terms of the buckets, the biggest driver is, of course, material. So yield is a big, big factor.
That's a
The
big
other
factor.
factors that we've seen from our own, trying different use cases are these. So one is yield, Of course, KGD does play a role depending on the assembly sequence and what types of tests you're doing in each intermediate step. The other big factor that's a knob is forecast volumes. If your volumes are not high enough, you may not see a huge benefit of doing chiplets, for example. But if your volumes are really high, you see a big delta. So notice in this chart, as an example, the reason why there's a big delta between the two options you see here from year 3 to year 5 is because you've gone from like 100,000 units to 1 million units. So it's that trade-off between yield and volumes that makes a big impact. And then the subsequent second-tier factors are things like IP interface cost and test costs.
Yeah. So I think, you know, that's my observation. Like, so you want to get that one right, basically the yield. I think is if you can get, and you're right, the known good die, all of that stuff, I would consider part, you know, part of that yield equation. Otherwise, you might get a very tilted view of this, you know. Like if I'm trying to determine how many dies I'm gonna need to break something, you might get a very tilted view, right?
Correct. And
Okay.
again,
Just one question. This is Ravi. The materials, which is about 83% of the cost, Mike, what do you include in the materials? Is it silicon wafer, assembly materials, both?
yes, substrate, silicon wafer, materials, all materials.
And is there a breakdown between materials? What is the substrate constitute that 87% versus what silicon constitute?
We can add that. We don't have that yet. Right now, we've lumped it only into materials, but if you would like a breakdown of substrate versus silicon, that's something we could incorporate.
Again, I don't know how difficult that would be, but
no, it's not. It's not. We can do that.
So where is the input in this? So material, it shows $88 million. So where is the input? Like, is it manual input? The B3?
None of these values on this page are inputs. This is the calculation. This is everything output. The
Okay,
inputs
so where,
are all here. This is the inputs. So here's where you're entering the wafer price. So this is your wafer price. And you're entering substrate price and you're entering NRE. All of those details are entered.
Okay. Yeah, I know you covered this. My bad.
Yeah,
okay.
Yeah. So all of this is the inputs. And you're right. I think what we should do is we should label this as output so it's very clear. Everything else is inputs. And that's where we capture it. So, but if you would like a breakdown that shows the contribution of substrate and silicon to the overall material cost, we can include that.
I think it may be useful in some cases where your substrate cost will increase because now you're going for a chiplet, you're adding interface area, so you need all the keep out zones. So maybe your substrate is becoming bigger.
Yes,
I mean, it may not apply to every use cases, but in some use cases it will be relevant.
Correct. Yes, absolutely. And that is something that is captured in the model, but it's not explicitly illustrated on how much more contribution you're getting from the substrate cost. That's something we can.
Hey, Dasar Distelko, just I want to point something out, and then I have a question too. But in your data input, you know, in this particular case, it shows that the chiplets model is leading to a higher price. But if, for example, you already had available chiplets from a previous project and you're reusing them, then your cost inputs would be much lower. And that's, of course, one of the advantages of chiplets over time is the ability to do some reuse. Am I saying that correctly?
You're right. Yeah, you're right. Absolutely. Yeah. So you could use this, again, this is a cost model. It's a tool. It doesn't take into account the context of your business use case. You may, for example, in the case you may have a chiplet that you've already paid for, and you're just using them in a new package, in which case your NREs could become 0. And so what you would do in this case is you would just go in there and say, okay, my NRE values, I already designed my chiplets. I'm not going to do that again. So you zero those out. Whereas if you're doing it from scratch, you may add those NRE values. So yes, absolutely. What you're saying is correct. And that needs to be captured by the user as they're inputting the values in the model.
Okay.
Right. So, for example, if you're a company that makes your own chiplets, then the NRE cost includes the R&D design plus the NRE mask cost. And if you're reusing it from already proven silicon chiplet, then your NRE design cost therefore is zero at that point.
Exactly. Exactly. Okay. Then the other comment I had on the packaging inputs, I like the way you have multiple stages where you can yield. I think as part of the sandbox work, and I can help you guys with this. One of the things we should add with that, though, is that the material content will change. So, for example, you're just calculating a compound yield at this point. But if you, for example, held off on adding HBM dies or optical dies or whatever till a much later stage, then your costs at each of those yield stages are going to be quite different. So just using a compound yield across the total cost is not necessarily going to give you the most accurate result. So if there's a way to allocate costs, what materials are included at each of those yield steps, it's going to help improve the accuracy of the model.
So Elko, that's a very, very valid point, and we do include that. So here, the zeros and one you enter over here will determine which materials you're using, and it automatically computes your cost consumption based on those specific materials. So for example, in the beginning, if you only used, if you just used one main die, and then you attached, the remaining dies, but you didn't put that together on the substrate, it will take just those into account. So this calculator here does exactly what you described. But of course, we do need to have the inputs of the yield for each assembly step. But once we have the yield inputs for each step, it automatically takes into account which materials and consequently which costs are consumed in each step.
Okay, I understand now. Thank you. Yeah, that makes sense the way you've got it laid out.
Elko, I actually had a question for you. So, Mudasser, could you go back to the same tab you were on? So if you look at the columns BA through BE for package assembly cost, it's really one lumped number. It's, this particular one says it's $20 per unit for the case that Mudassir is modeled in this particular spreadsheet. Is that easy to do? For example, if I'm trying to compare going organic laminate MCM style to a silicon interposer to using RDL without an interposer, can I actually ask you to, say I've got these 3 chips. Can I say, hey, Elko, can you give me one number that I can put in there? It's $20 for an MCM, it's $40 for silicon interposer, it's $30. Is that really correct? This kind of lumped number there?
It would require some work. I mean, the way we typically quote is there's wafer-based services such as, bumping and wafer sort and middle end of line processing for the interposer versus unit-based costs such as packaging and final test. So it would take some math on the part of the user to get working with the OSAT to convert that to a unit cost. So if in future efforts, that's something we might be able to build out a model for, right? Just have a tab for the assembly unit costs where we come up with what are the different contributing factors that are going to go in there, right, so that you come up with that.
Yeah, exactly. Thank you.
And then, one comment on the test that I was going to make, I think there was a comment on repair, and, there's also the retest question. One simple way to maybe try to deal with, redundancy for repair, et cetera, is just to have kind of a recovery factor that, so if you use your base yield models, whether it's Murphy or Bose-Einstein, and if there's redundancy, then you could have just a yield factor adjustment that you call a recovery factor that results from the fact that you have redundancy, or same with the retest side. So that might be a simple way to account for that yield shift.
Perfect. That's exactly along the lines that Javi and I were thinking about. We could put in a recovery factor. We could make it a little more sophisticated because we have to decide what level of detail we want to go into. If we just look at time zero yield, we can use a recovery factor and say, okay, this is how many we would still be able to utilize, and that's commonly done. It's convenient way to do it, and I'm glad you validated that for us. The next one would be, okay, so let's say I added 4 redundant cores, and now because of whatever yield loss I had, I consumed 2 of those 4 redundant cores. Now when I'm running during the operating lifetime of the device, this has consumed 2, it only has 2 redundant cores left. Another one might have 4 redundant cores left. And after about a year, something fails, it has consumed the remaining 2. And now it's going without anything left. How do we capture that reliability evolving over time, intercepting with the redundancy that's left in the device after it's been finally yielded? So that's the piece that we're still evolving with. We're not
but quite honestly, on that second case, I mean, if you are the product supplier and you're providing a product that meets a certain spec, which would include, a defect over time kind of warranty, then how you get there is maybe not as germane, right? I think the key is for the chip maker to input whatever they need to achieve that. So if they say, hey, I'm going to make my die slightly bigger so I have 4 extra cores, because that way I know I can meet the requirements of the part in the field. So I hear what you're saying, but I think you have to look at it from the other side as well, right? At some point you've got to assume the chip supplier is doing what they need to meet the defectivity rates.
Correct, and that you're absolutely right. So what we're likely going to do is we'll initially begin by adding a simple factor, so that the model allows people to have the ability to capture redundancies. And then we'll see if people are okay with it, we'll let it be at that level. But if people ask more questions and would like to incorporate some additional features, we will then revisit and see if we can incorporate things like reliability over time and whatnot.
Makes sense. Thanks.
All right, cool. So again, we will share this with whoever is interested. Bapi, please let us know what is the mechanism with which people can ask. We don't want to open this to everybody and anybody at the moment because, again, it may raise more questions than answers, and it's hard for us. We're a volunteer army of 3 trying to do this. So we need to triage and get those people who are actually playing with the sheet to give us inputs and then use that information. So it would be helpful if one person could consolidate and let us know who wants access to it. Of course, Bapi can always post the link online and people can play with it. But in terms of giving us feedback, it would be useful if we had a more streamlined mechanism for getting that feedback.
So, there's sort of three options. One is to just make the business working group the place where this happens for now. The second is to post the link, but not make it a public link. So somebody clicks on it, they'll have to ask you for access, and you can sort of decide who gets a beta. And the third is to sort of make 2 copies of this. One, the working copy that you guys are working on. The second is sort of the release copy that people can play with as they choose. I'm okay with all
Bapi,
3.
we'll probably do all 3. We will release just a production version that is open for others, which will not be our internal version. And we will definitely make this part of the business working group. And yes, we will be able to set it up in a way that anyone who wants access can request access and we can provide it.
Are you going to publish any notes on the algorithm for that cost model?
When you say notes on the algorithm, can you be more specific?
Like, for example, how do you get the final cost? Is that just addition of all these total costs? Are there dependencies between these 2 costs?
So right now what we have in this factors page is we've given explanations for each of them, but we've not added the algorithm portion yet of what exactly it rolls up to. But to answer your specific question, the total cost is a roll up of all the base costs, and it's
Roll
worked
up
through
meaning
here.
just admit a sum.
Addition, a sum, yes.
Okay.
There is some sophistication in the way the KGD is calculated because it takes into account each assembly step and all that. So if someone is comfortable enough with Excel, they can pretty much work out what it is in the sheet. That's the reason we're using the sheet, so that the calculations are transparent and anyone can know how they've been computed. But we haven't planned on writing like a document that rolls up the algorithm at the moment. It's something we can think about incorporating as well.
Sure. Thank you.
Hey, Mudassir.
Yes, ma'am.
Couple of questions. In terms of help, maybe, so I'll throw an idea out for what it's worth is maybe you guys can consider an opens tab where you list all the specific things you're looking for help on as part of the spreadsheet. There's, we're looking for help on yield model for this or something, and somebody can, then the people using it have a sense of what it is that you're looking for, or what we're
Yeah.
looking for, excuse me.
It's a good point. We can do that. Yes.
The second one is like a little bit of more a question again. I found it helpful to have inputs in blue or whatever color of your choice. And so you know where exactly where, unless you guys already have the input somewhere tabbed in.
So here's where we have a legend that says this is the user input color.
The green. Okay, thank you. Perfect.
So this legend is what we're using throughout for consistency. So
Awesome.
anyone who sees this color, it's an input.
So the one then the third one is there's a lot of merit to the idea of a white paper or some other write-up on this to accompany this. It's a decent amount of work, but this looks like a fantastic model. And if you had like either a web repo or hanging off the OCP GitHub or something like that, which says this is how you, this is the thinking that went into the model, or a formal white paper, there's be a huge amount of value in that.
Yeah, so we've sort of toyed around, but we haven't, I mean, depends on our bandwidth and resources. We've gotten the abstract submitted for the OCP summit, and we got the email yesterday confirming we will be presenting this. Towards that end, we may put together a white paper that essentially rolls up the algorithm and the factors and how we've combined them together. And also what we'd like to do is, again, this is step 0. We're sort of just putting out a simple model to begin with. But eventually there's a roadmap where we're hoping to incorporate this with other factors into taking into account where you would have the sequence of the assembly captured in a numerical way. You can then assemble a whole complicated package, and you can do a bunch of sensitivity analysis, which would essentially convert this into like a Python script that we would release as a GitHub repo. Anyone can download and use it to do a bunch of sensitivity analysis to say how sensitive is my model to the price or forecast or yield or assembly steps or KGD and all of those things. So there's a set of things that we are looking to incorporate later that would essentially take this model to a level of sophistication that it could be used for day-to-day activities for even during the design process itself. So we may capture that roadmap as part of that white paper as well.
Oh, just awesome. Okay. That was one thing I forgot to mention in the lead up was that this is the, if I have it right, this is the first outcome from the newly energized business group that Ravi and DJ started based off the workshop we had.
Thanks, Bapi, but I don't want to take any credit here because I think Mudassar and Harvey and I think Anu did the most of the work here. So, but one thing I think this is awesome from a community contribution standpoint. I don't think anything of this magnitude exists in the community. We just need to find a way. How can we make it more public so that more and more people can use it? And maybe we can brainstorm in the business work group.
Correct, and I do think credit is definitely due both to DJ and Ravi because it helped us at least collectively agree that this is a high priority. That itself was a challenge in the business working group, and that prioritization helped drive us to be able to deliver something that we could use. So no, thank you, and I think the business working group helped corral a lot of inputs to help get this to this point.
Yep, I totally agree with Mudassir because, I think DJ and Ravi tried to sort of herd the cattle to try and settle on what is the number one priority, number two priority, and after establishing that, people could put energy towards it. So yeah, it's that's the beauty of open source, I guess.
So guys,
You
just
know, this is
FYI,
really,
what takes normal mortals a week to write, how we can polish it out in a day. Just FYI.
Oh, we figured that out a long time ago,
Yeah,
Ravi.
exactly.
Yeah,
yeah,
we
this
can
is,
spit
by the
stuff
way,
out
very
at
good.
like terrific speed. Yes.
This is very good. I think if I were to tease you a little bit, maybe a next step, and maybe we can talk offline since you already have some really good model and infrastructure, all this data. Have you thought maybe to include things like performance and power? Because most people, they look at cost, performance, and power. So if I break, for example, a big die into multi-chiplets, this would be a very good model to tell me, okay, that's the cost between this or that. But if I were to run a benchmark, for example, what would be the impact of that breakage on performance, on power? And I think probably an extension, if you could add that, then you have really, really, I think, a very, very powerful tool that gives you all basically cost, area, performance, and power. And if you
Taufik,
want to think that way, I'm happy to talk to you offline because I have some expertise in the latter part of it, basically the performance and power modeling.
you're absolutely right. I think PPA would definitely be much more powerful. We initially, of course, wanted to start humble and stick to the business and cost side of things. But when you start normalizing that against performance and power, it does provide a bigger value. So more than welcome. Please, join us. We would like to take you up on the offer and talk to you offline on how we could further enhance this by incorporating the power and performance part of it as well.
Sure.
So,
Okay.
hi, Mudassir, Anu, and Harvey. This is an excellent work. I'm JP. I have one question. Are there any tools available existing today to do this kind of modeling, commercial or any other tools?
So I can answer at least there are tools which exist more you have to take a license, but not to this level. There are tools which do more, at least what I am aware of. But mostly most of the company have their own cost modeling by which they do more this kind of stuff. And in a public domain, there are some licenses I have seen which exist. But to me, this is the most comprehensive one which I have seen in an open source.
Okay.
So to Ravi's point, JP, as he said, there are commercially available tools. You can purchase a license for them, and we actually initially did speak to some of those folks because none of us is interested in building something that already exists, and we would prefer in many ways if someone can take this and just provide it, or even if they charge a nominal fee for it, it would be worth it because they can maintain it, they can run it, and they can provide inputs and enhance it. It's more scalable for them. However, what we discovered is that the current available tools can be bucketized into two categories. One is there are these commercial sort of proprietary spreadsheets, but they are focused more on determining wafer costs and wafer pricing. When you want to look at chiplets, the big unknown is that assembly sequence. If I mounted 3 chiplets together on a 4th interposer and put them all on a package, that sequence of mixing and matching and assembly process and the KGD part of it is not something that is currently available commercially. And so that's the reason we had to embark on this exercise to put together a way that can capture the chiplet part of it. And we have not seen any roadmap to providing something like that commercially at the moment. If, of course, someone decides to do so, that's always something we would welcome because it can make things easier, especially if it's not that expensive for them to do. But that's the challenge we've faced. That's one bucket. The second bucket is there are people who do their own spreadsheets, which are proprietary. But the problem there is that think of an ecosystem when you have a device aggregator or an OSAT or a foundry or even the end user. Each one of them is doing their own proprietary sheets trying to analyze the exact same problem. And half the time, the assumptions in each of those spreadsheets don't match. And so they never actually have a common base against which to compare their models. And what we're hoping to use with this is a common model where anyone can enter their own data, but at least some of the factors they take into account are common. And so it helps speed up that conversation on whether it's worth it or not worth it, especially early in the design phase, when you're still trying to see the trade-offs and seeing whether it's worth exploring doing chiplets in a certain configuration.
Mm-hmm. Okay, so the benefit of this tool is actually find the relative cost between the two architectural options.
Correct. If it has, that is a very important benefit because you can do pairwise comparisons. But also, if you're trying to sell a device, if someone is trying to sell this particular hypothetical chip for $1,000, they can see that it's not going to happen. And so they can then have the conversation of, okay, if I actually make this work and I'm aiming for a gross margin of at least 20%, I have to sell this chip for around $1,200. Is there a market for it? Will anyone buy it? If I do sell it, how much volumes can I actually generate given the price point I'm selling it at? So those business conversations can happen as well. And it can speed up that discussion earlier. A lot of times the trade-offs are between volumes and yield. If you talk to a typical marketing department, they would generally be very optimistic and say, yeah, we'll be able to ship X amount of volume. And you talk to the yield guys and they'll be very pessimistic and say, well, you'll be lucky if you get a one device in the beginning, right? But the challenge is always achieving that optimum between those two extremes. And we're hoping this type of a model can help achieve that more efficiently.
Okay, very nice, Mudasser. Thank you.
Yeah, it'll get even more complicated if, like, you take, say, bin split into account. For example, are you consuming all the die? Are you doing multiple performance bins? And but I can see that model, starting this way and getting, quite sophisticated. I mean, I came from Intel. Of course, that's what Intel does. So we had our own internal tools, to do stuff like this. But I think it's very promising.
And I think that's where some of the conversations are really powerful. Like if you skewed this, if you had more, versions of it, if you were binning it and you were selling different bins at different pricing, you can enhance this and use this as a module into those complex scenarios as well.
All right.
Okay.
Thank you. Thanks, Mudasser, Anu, Javi. And if you'd like to, please send me a link. I can add it to the minutes. Otherwise, we can. We are done. If there's no other questions.
Sounds good. I'll send you the link. Thank you.
Thanks, Mudasser. Hey, Ravi, I'm going to add it.
Bapi, just one comment. So I think this is an excellent amount of work. And at some point in future, whenever a community feels ready, especially based on Anu, Javi, and Mudasser's approval, we should look at publishing this on the OCP GitHub, on the ODSA, with README notes and stuff, whenever it becomes possible. I think that way it can get even broader exposure and the press can pick it up and then everyone can recognize the work which is being done in ODSA. So just a thought.
Totally. Okay, I think this brings our meeting to an end.
This conference will now be recorded.